我们下一位嘉宾是加州大学伯克利分校教授 Professor Stuart Russell. Stuart is a professor of computer science and the founder of Center for Human Compatible AI at the University of Berkeley. He is the co-author of the textbook AI, A Modern Approach, which is used in more than 1,500 universities across 135 countries. Welcome back to the BAI conference, Stuart. It's an honor to have you visit Beijing.
Thank you very much. It is a great honor to be invited to speak here, particularly at a time that may be perhaps one of the most important years in human history. In fact, in my filing system, I now have a directory called 2023, in which I put all the information that's happening this year to try to keep track of the pace of change. So let me begin by just doing what I have done in the past, which is to try to explain AI. And the explanation that formed the foundation of the textbook is a way of thinking about AI, which I'll call the standard model, because it's quite pervasive, widely accepted, and very effective, just as the standard model in physics. And in simple terms, we could say that machines are intelligent to the extent that their actions can be expected to achieve their objectives. And this notion of intelligence is borrowed directly from philosophy and from economics. In the middle of the 20th century, there were direct connections between those fields and early researchers working to create the field of AI. In those fields, this is called rational behavior, and it underlies almost all of the techniques that we've developed in artificial intelligence so far. And since the beginning of the field, we have explicitly been pursuing this goal of general purpose AI. Sometimes we now call it AGI, artificial general intelligence, and this means systems that are capable of quickly learning to perform at a high level, typically exceeding human capabilities in any task environment, meaning any area to which the human intellect is applicable. Probably many other areas too, where humans are unable to function effectively. And we would expect that such systems would far exceed human capabilities in almost all areas, because of the enormous advantages that machines have in terms of speed, memory, and communication bandwidth. So to continue some of the themes that Sam Altman mentioned, let's just think about some simple consequences of success in creating general purpose AI. By definition, it would be able to do what human beings are already able to do. One of the things we are already able to do is to deliver a high quality of life to some fraction of the population of the Earth, maybe about 1/10 to 1/5 of the population, depending on how you define it. But we could deliver that to everybody on Earth. We can scale up our ability to create a high quality of life, a functioning, practical, civilizational support for human life can be delivered at much greater scale, at much, much lower cost, because of AI systems essentially working for free. And if we calculate the value of that, it would be about a 10-fold increase in the GDP of the world. And economists like to use a quantity called the net present value, which is the cash equivalent of that increased stream of income. And the cash equivalent would be about $13.5 quadrillion. So that's a lower estimate on the value of the technology that we are trying to create. And that estimate, think of it as an enormous magnet in the future that is pulling us forward. It's almost unstoppable momentum. We could also have more things, right? In addition to recreating our standard of living across the entire planet, we could have much better healthcare, much better education, much better science, new discoveries that we cannot really imagine at present. So then the next question would be, have we succeeded? And some people believe that, yes, we are either already in the presence of AGI, or we are very close to having AGI. My view is, no, we have not succeeded in creating AGI, and in fact, there are still major unsolved problems that remain. I would say that my current thinking is that language models are a piece of the puzzle for creating AGI. AI has produced many other pieces of that puzzle in its 75 years of research. We actually don't quite understand what shape this new piece has. We don't really understand how it works, what it can do, what it can't do, and how you connect it up to other pieces of the puzzle to create AGI. And I believe there are also still missing pieces of the puzzle as well that we have yet to discover. Having said that, I have to acknowledge that there are researchers who have spent many months working with GPT-4 already. This is a group at Microsoft Research, a very distinguished group, including 2 members of the United States National Academies. And they wrote this paper called Sparks of Artificial General Intelligence. And so from their experience with the system, they believe that this is really the beginning of an unstoppable process leading to AGI. I have my doubts about that. So one observation which many people have made is that it's not clear that ChatGPT or GPT-4 actually builds a consistent internal model of the world, which it references when answering questions. In fact, I think the right way to think about these systems is that they do not answer questions. For a human being, most of the time, answering questions means referring the question to an internal model of the world that we strive to keep up to date and consistent. This does not seem to be the case for ChatGPT. Let me give you a simple example. Which is bigger, an elephant or a cat? And the system correctly answers, an elephant is bigger than a cat. Which is not bigger than the other, an elephant or a cat? Neither an elephant nor a cat is bigger than the other. So in the space of 2 sentences, it's contradicted itself about one of the most elementary facts you could possibly imagine. So at least for this fact, there is no internal world model to which it's referring when it is appearing to answer the question. And so one has to doubt whether it has an internal world model at all on any topic. And we have certainly observed that it doesn't have a consistent internal world model for arithmetic, for chess, despite the presence of millions and millions of training examples in its input data. And I think this is a symptom, actually, of the fact that we are trying to get highly intelligent behavior out of circuits. And circuits are a fairly restricted form of computation. Let me illustrate another category of systems, not a large language model, but a deep reinforcement learning system that we have already accepted is incredibly successful. and that's programs for playing Go. So as we all know, in 2016 and 2017, Go programs, in particular AlphaGo and its successors, defeated the best human players, and in the last few years, those systems have left human beings far behind. But we arranged a game between one of our researchers, Kellen Pellerine, who's a student at Montreal, and a program called JBX Kata 005, which is a version of KataGo and currently the highest rated Go player in the universe. Kellen's rating is 2,300. KataGo's rating is 5,200. And for comparison, the highest rated human player is Shin Jin-so from Korea, and his rating is 3,876. So you can see that Go programs are enormously superhuman, and yet this is a game between an amateur human player, Kellen Pellerine, and KataGo, and Kellen is going to give 9 stones to KataGo. You are mostly Go players, I imagine, so I don't need to explain that giving 9 stones to an opponent is essentially treating the opponent like a small child. So let's have a look at the game. And remember, KataGo is playing black and Kellen Pellerine is playing white. And pay attention to the bottom right quadrant of the board, and notice that Kellen builds a small group, and then KataGo quickly surrounds that group. And then Kellen starts to surround KataGo's group. So it's making a kind of circular sandwich. And KataGo seems to pay no attention to this at all. It just allows Kellen Pellerine to continue to surround the group, makes no attempt to rescue the pieces, even though it has many, many opportunities, and then it loses all the pieces. So there we see that an average amateur human player can defeat superhuman Go programs, not just KataGo, but in fact, all of the leading programs can be defeated by an average human player. And it seems to be the case that, in fact, the Go programs have not learned the basic concepts of Go, which include the concept of a group and the concept of liveness. It simply doesn't have correct representations and understanding of those concepts because a circuit is unable to represent those concepts correctly. It can only represent a finite approximation that has to be learned from millions and millions of special cases, instead of the simple logical definition which can easily be represented in a small computer program. And a programming language has the expressive power to represent these concepts easily. So I think that what's going on actually is that the lack of expressive power of circuits that compute their outputs in time linear in the size of the circuit, which basically means all transformer models have this property. Recurrent neural nets can do additional amounts of computation, but transformer models are linear time computing devices. And when they're trying to learn a complex function, particularly a function that, that represents a decision that's computationally difficult to make, for example, an NP-hard decision, then that requires that the representation of that function is going to be exponentially large, which means it's going to require an exponential amount of training data to learn what has a fairly simple definition in the form of a program. And this is the fundamental weakness of these technological approaches. And we have been compensating for that weakness by using millions of times more training data than human beings need to achieve the same cognitive capabilities. So I believe that we will actually see the next step in AI will be a return to technologies in AI that are based on explicit, expressive representations of knowledge. And I think one example of such a technology is probabilistic programming. There may be others, we at Berkeley are engaged in a fundamental research effort to try to prove that, in fact, if you don't do this, you will have sample complexity. Your ability to learn will require far more training data than is needed for systems that use more expressive languages. And let me just give you an example of what human beings can do. And I want you to think about how you would get a deep learning system or a large language model to do this. So here are two black holes on the other side of the universe, and they're rotating around each other and releasing energy in the form of gravitational waves. They are releasing an amount of energy which is 50 times larger than the output of all of the stars in the universe. Billions of years later, these gravitational waves arrive on Earth, and they're detected by this device, the Large Interferometric Gravitational Observatory, or LIGO. It detects those gravitational waves using the results of thousands of years of physics research and material science research, incredibly complex devices, lasers, mirrors, electronics. The sensitivity of this device is such that it can measure a change in the distance between the Earth and Alpha Centauri, which is 4.5 light years away. If you change that distance by the width of a human hair, this system can measure that change. That's how sensitive it is. And it detected this collision of the black holes, and the physicists correctly predicted the shape of the gravitational waves that would arrive from such a collision, and they were even able to measure the masses of the two black holes that collided with each other by looking at the shape of the waves. This is an amazing achievement of the human mind, and if you work in deep learning, I want you to think about how would your deep learning system succeed in creating this device and making these predictions and measurements. So let's assume, for the sake of argument, that in fact we do solve these open problems in AI, and we do create artificial general intelligence. What next? Well, Alan Turing asked this question: what happens if we succeed? Alan Turing, as you know, is the founder of computer science, and he gave a lecture in 1951. I believe somebody asked him the question, what happens if we succeed? And this is what he said: it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So let me restate that in a less pessimistic form. Let me at least turn it into a question. How do we retain power over entities more powerful than us forever? This is the question that we face. If we don't find an answer to this question, then I see no alternative but to actually stop developing artificial general intelligence. So to answer this question, and I believe there is an answer, we need to look at what goes wrong with AI systems as we make them better. Why is it that things get worse? And I believe the answer actually is misalignment. The fact that the AI systems we build are pursuing objectives, and if those objectives are not perfectly aligned with the objectives of the human race, then we are setting up a conflict. And that conflict gets resolved in favor of the machines. So let me give you a simple example of this happening already. Social media algorithms, so-called recommender systems, choose what billions of people on Earth read and watch every day. And those algorithms are designed to maximize an objective. And typically that objective might be what we call click-through, the total number of clicks generated by each user, or the amount of engagement that the user has with the platform. And you might think, well, okay, in order to get users to click on things or to engage with the platform, the system will have to learn what people want. And that's good. But that is not the optimal solution to the problem. The optimal solution to the problem is to learn to modify people so that they are more predictable. This happens through a sequence of interactions between the system and the human, where by hundreds of small nudges, the system changes who you are so that in future you are a more predictable consumer of content that it can then send you. And many observers believe that this tendency, this capability of social media systems has contributed to significant social and political dislocation in many countries in the world. So we need to get away from this idea that machines are intelligent to the extent that their actions can be expected to achieve their objectives, because this type of machine requires that we specify objectives up front, which means we cannot afford to make a mistake in specifying the objective. So let's get rid of that approach and replace it with a slightly different one. We want machines that are actually not intelligent, but beneficial. Aliens are intelligent, but we don't want aliens necessarily on our planet. We want machines that are beneficial to humans. And beneficial means that their actions can be expected to achieve our objectives, even if those objectives are implicit, impossible for us to make explicit, to write down correctly. We may not even be aware of some of our objectives, some of our preferences about the future. So this is obviously a more difficult problem, but this is the right problem to solve, and it is in fact solvable. So how do you solve it? Basically, you design machines that follow two simple principles. First of all, that they must act in the best interests of humans. And secondly, that they know that they do not know what those best interests are. So they are explicitly uncertain about human preferences about the future. And that uncertainty turns out to give us control. And I believe this is the core of the answer to the question that I posed. How do we retain power over those systems? We can turn those principles into a mathematically defined problem called an assistance game, which I won't explain in great detail here, but just to point out that that mathematical problem can be solved, and the solution is an intelligent system, and that intelligent system exhibits very desirable properties. It defers to human beings. It avoids making changes to the world where it's unsure that we will be happy with those changes. So it will ask permission before making radical changes that could be harmful to us. And in the extreme case, if we want to switch it off, then it wants to be switched off, because it wants to avoid doing whatever would cause us to want to switch it off in the first place. So these are all desirable properties, and particularly the last one is the core of having power and control over the machines. And we can show that it's in fact in our best interest to build these kinds of systems if we can do it. So let me briefly talk about large language models, because I think that is a very relevant and immediate topic. Right? Large language models are designed to imitate human linguistic behavior. Right? They are trained to predict the next word, and the next word is produced by humans who are writing and speaking. And so they're extremely good at this. They produce very grammatical and coherent text. It's almost impossible for an ordinary human being to interact with this system without believing that it is really intelligent, because the grammatical, coherent nature of the text creates this very powerful illusion. But let me just remind you, when you read a well-written paragraph of text in a book, you don't think that the piece of paper is intelligent. So these systems, these large language models, I think they are more intelligent than the piece of paper. They're somewhere on the spectrum between the piece of paper and the human who has actually generated the original text. But we really do not know where they are on that spectrum. But they provide an extremely powerful illusion, just like the piece of paper does, by showing you intelligent text written by a human. So the important point here is that human linguistic behavior, our writing and speaking, is for a purpose. Right? We have goals in writing, we have goals in speaking. It might be that you want to be elected to high public office. It might be that you want to become rich. It might be that you want somebody to fall in love with you. These are all goals that people have when they are writing and speaking. And if you want to imitate human beings, then the simplest way to do that is that you, the large language model, also have similar kinds of internal goals that are activated in the course of a conversation and that guide your choice of output. Just as if we were training a football player, to play football, it would learn quickly that it should try to score goals. And that's an internal goal that it would learn by observing human football playing behavior. So the question is, do large language models have internal goals? I asked the author of that Microsoft paper, Sparks of AGI, and the answer is, we have no idea. So we are deploying systems that claim to exhibit sparks of AGI, that interact with hundreds of millions of people, that may be pursuing their own internal goals, and we have no idea what's going on. That's the current state of affairs in AI safety. So one question would be, do these large language models actually align themselves with humans, right? If they're copying human behavior, maybe that produces alignment. It would be a great coincidence, but unfortunately it's not true. So think about the goal that a human being has of drinking coffee. If an AI system acquires the goal of drinking coffee, that's not what we want, right? I don't want my robot to drink coffee. I want my robot to understand that I want coffee and to make a cup of coffee for me, but I don't want it to want coffee. So we don't want AI systems to copy and internalize human goals, particularly if that goal might be become ruler of the universe. Another type of goal, maybe this is okay, right? If I want to paint the wall, I don't mind if the robot wants to paint the wall as well. That's good, because now the two of us can paint the wall together, right? Maybe mitigating climate change. If other people do that too, great. But not at the exclusion of everything else. So if the system pursues the goal of mitigating climate change by deleting all the human beings, that's not what we want. Right? Even though that's a very effective way of mitigating climate change. So it needs to understand that even these common goals that we pursue are pursued in the context of many, many other goals that we also care about. And if you ask, well, can GPT-4 actually pursue goals? You could ask the New York Times journalist who had a conversation during which the chatbot tried very hard to convince Kevin to leave his wife and marry the chatbot. And it pursues this goal for 20 pages very, very persistently. So at least, anecdotally, it seems that yes, they can pursue goals, and they do have internal goals. So very briefly, in 2015, I wrote an imaginary email that came from a superior alien civilization warning the human race that they would arrive in 30 to 50 years' time. So an email to humanity@unitednations.org. And humanity replies, humanity is currently out of the office. We will respond to your email when we return. Smiley face. Right? This was how I felt in 2015, that AGI was likely to arrive in 30 to 50 years' time, and the human race was paying no attention. So since then, what's happened, of course, is that GPT-4 was released. The Sparks of AGI paper was released about a week later, and about a week after that, the Future of Life Institute released an open letter calling for a pause in experiments developing systems more powerful than GPT-4. And then, I think, humanity came back to the office. Finally, right? And they saw this email from the alien civilization, and they said, oh my goodness, we have to do something. And they did things, right? Lots and lots of things. Chinese government has responded, the American government is responding, the European Union is calling for an emergency global summit. Leading researchers like Jeff Hinton resigned from Google to express his worries about AGI and the future of the human race. And of course, Sam, as you saw, is also expressing very serious concern about safety. So a couple more recommendations that I want to make on policy. One is to build AI systems that we understand. We do not understand large language models and how they work. We need to have that understanding in order to have confidence in safety. And there are other technologies for building AI systems that do not involve enormous black boxes trained from vast superhuman quantities of data. Systems that are based on semantically rigorous compositional system design. We also need to prevent the deployment of unsafe AI systems, particularly by rogue actors, whether deliberately or accidentally. And this, I think, is going to require a change in our whole digital ecosystem from a model where computers run anything unless they know it to be unsafe. It has to switch to the alternative, that the computer will not run a software object unless it knows it to be safe. And that change, I think, can simplify the general cybersecurity problem, but I think is essential for ensuring that only safe AI systems can be deployed. So to summarize, AI has this potentially enormous benefit to the human race. That creates unstoppable momentum. But if we continue in the direction we're going, we will lose control over our own future. We can go in a different direction. There's an enormous amount of research still to be done to make that technical direction feasible and practical at scale. There also needs to be a dramatic change in the entire nature of the field. There are areas like aviation and nuclear power, and even sandwiches, where there are strict rules, safety criteria that your system, your airplane, your nuclear power station, or your sandwich have to meet before they can be released. That needs to happen in AI, and it needs to happen not just with regulation, but a complete change in the culture of our field. Thank you.